Here we are getting into this area of probability. And like I said in the opening statements for this section in Moodle, we're going to try and marry probability theory, and again, just the basics of probability theory in with what we call testing research hypotheses. And they may seem a little bit separate from one another, but they really do combine together. And so this is going to form kind of a, how should I put this? If we were making, if we were baking a cake, this might be the eggs and the flour, so to speak. You kind of need it to kind of hold things together. This is going to form the basis for when we move into chapter 8, which is the normal curve. And that's where probability is going to show up again. You'll see it happen there. And also, this is going to set us up a little bit for chapter 9, where we start getting into what are called type 1 and type 2 errors with respect to research decisions that researchers make. So this is the first part, probability primer, and then we move into chapter 7, where we start getting into what is called the research hypothesis and the null hypothesis. So here's this area again that I've highlighted in yellow, and it will make more sense later on when we get into making statistical decisions. And this area that I have in yellow is this. An important factor for you to remember is that things can happen randomly, or as we call it, by chance. And by chance, we mean it's a series of things that happen without any kind of systematic design in place. You want to think about chance that way. Things can occur without any type of systematic design that has been in place in order for that occurrence to, or that happening to occur. That's kind of hard to put into words. Okay, so that's what you could probably look at that as a definition of chance. Things that can occur without the influence of any kind of systematic design that has been set in place. And we actually have to start there for a basis, because in research and in research articles that you read, what you're actually examining are the systematic designs that researchers put into place to show an outcome. I mean, that's what research journal articles do. The whole methods section, when you read a research journal article, is the systematic design to influence some sort of outcome. So outcomes do happen because of systematic design, and we see those in the methods sections of journals, but outcomes can also happen randomly by chance. And so what a lot of research does, and what statistics do, is it partitions out how can we be confident that the occurrence that we had here, whatever this was, someone did better on a midterm score, or someone's temperature went down. How do we know that actually happened by some sort of systematic design, i.e. studying tutors, right, for a midterm score, or acetaminophen for temperature? How do we know it was those factors that caused that and it wasn't by chance? That's really a large essence of statistics. That's what we come back to time and time again. Did it happen by chance, whatever we see happening, or did it happen by some sort of systematic design? So this is why we have to spend some time describing what chance and what probability is all about. Now, the normal curve associates us with the basis of understanding the probability associated with any possible outcome. The normal curve actually gives us a percentage that something happened by chance, right? What is the probability? And so probability is complex. The math is unwieldy. It's not a lot of fun, but nevertheless, it's an essential concept for us to understanding statistics, in particular inferential statistics, right? When we go from sample to population, that becomes really important. And so you might have encountered terms like these or statements like these. There's a 50% chance that it's going to rain tomorrow, right? Or what's the probable chance of rain tomorrow? About 50%. 50% probability it's going to rain tomorrow. Or it might be a question. What is the likelihood that she gets selected for the scholarship? Like what are her chances? And so these statements have some type of meaning in the sense they actually help us make predictions in the case of the scholarship, Or in the case of the rain forecast, they determine actions, right? They determine actions. And so in the real world, we take what we find in research and we apply it to certain things, right? It might be a different way of studying, for example. Might be the application. Well, if you get a tutor to help you with studying, you've got a 30% increased chance that your grades are going to go higher. Now, 30% is actually pretty low. If someone told me, hey, Mike, if you get a tutor, the chance of you going from a B to an A in that class is 90%, right? It's not 100%, but 90%, that's a bit more interesting to me. A 90% chance over a 30% chance. And so this is why we use the terms likely and probably in statistics. Notice we haven't used the word certainty yet, right? And we don't. As a matter of fact, we don't use the word certainty. We use the terms probability and likelihood and chance. Those are the terms that we use, and we'll get to that as to why that is when we get to the normal curve. So let's give a definition for probability. Probability is the likelihood that any one event will occur, given all the possible outcomes. Okay? It's the likelihood that any one event will occur given all the possible outcomes. So in order to calculate probability, you need to know what the possible outcomes are. Now, in some cases, that's going to be pretty easy. Other cases, not so much. Probability also gives us some indication of an outcome or a future event. Okay? It's an indication. It's not certainty. Right? There's always going to be a gap there. This is why we say in statistics you can never prove something. Proving something means you're 100% sure. We can disprove something and leave something left over, and that gives us a likelihood that what is left over is the case. It gets a little bit weird with the language. I do apologize for that. Probability doesn't give us any guarantees, but it tells us the likelihood that something can happen at random. Okay? And again, just at the bottom part there, probability does not deal with events wherein skill or ability is involved in the outcome, or, in other words, no systematic design. Right? No systematic design involved. It's the likelihood that an event will occur, given all the possible outcomes, and it gives us some indication of an outcome or a future event, and does not involve systematic design. Carrying on from the previous slide, we said that probability can't involve anything that requires some element of skill. And that's true, because once you've done that, you've actually changed the rules, so to speak. But, you know, if we do something like a coin flip, there are some factors that do actually influence how the coin is going to land. Now, some of these things are within the control of the performer, some of them are not. So here's a few of those. I sat down and thought about this, and so here are a few. Number one, the amount of force that one applies to the coin. Now that's in the control of the performer, right? Where that force is applied, that's kind of tricky. Depends upon if I can balance a coin on my thumb. I'm usually not thinking about that, but some people might. The air density, that's not going to be in the control of the performer. Neither will air currents. Neither will how the coin lands, on what type of surface it lands on. Well, you could change the surface. You're going to have different outcomes. And there's going to be other things, likely unknown to us that are going to affect how the coin lands. And so the point of it is this, the likelihood that the performer can control all of these things to elicit some sort of outcome, a specific outcome consistently, is unlikely. There's going to be some things that we leave up to chance, especially those unknown factors. We can kind of sort out and hypothesize about what might be affecting a coin's performance, but there's going to be some other things that we don't know, right? And so this is why we say we leave things to chance. And the same thing can be applied to something like a die, right? So this time, instead of having 2 outcomes, now you've got 6 potential discrete outcomes that can occur. And this is how cheating occurs in rolling of die. Not that I gamble, I've never been to Vegas, but you can, if you can actually sneak it in, which is kind of hard to do, you can actually weight the die in a particular way, which means you change where the center of gravity is in the die itself. And that's going to elicit a greater chance or likelihood that the die is going to fall in a particular way and elicit a particular response. So you've taken out the chance, and when you take out the chance in Las Vegas, they call that cheating. Okay, so how do we measure the chance of something or the probability of something occurring? Now, the wonderful thing is we're still using the same values that we used back with reliability and validity. That is to say, it's going to be a value between 0 and 1. So if a probability is 0, the number 0 means not likely, right, or highly not likely, there's going to be a 0% chance of that event occurring. A number close to 1 means quite likely, or 100% chance or probability of occurring. So we could say then that probability values range from 0 to 1 and everything else in between. Now, as this slide says, the reality is that most things fall somewhere between impossibility, a p-value of 0.0, and absolute certainty, p is 1.0. Now, we said there's no such thing as certainty, at least in our discussion of statistics, which means there's also no chance of impossibility occurring as well. There's still a chance that something can occur or not occur, if you want to think about it this way. And so this again is going to be the range. In journal articles, if you've read them, you might have come across these values that you see down below here. Where's my little laser pointer? Here we go. You might have seen some sort of, if you actually read the results section, which can be really unwieldy to read, it's complicated. You might see a value where they state something, blah, 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 and then p less than 0.05. Or blah, 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 p less than 0.01, right? This is where we see probability expressed in the literature. So now we're trying to make this connection. Even for those of you who never want to do statistics or run research, when you're reading research, when you see this italicized p, right, with those values, you now begin to get a sense of the probability. Now, what I'm not going to tell you quite yet is what that probability is, because it's a little bit backwards, right? It's a little bit backwards. And I'm sorry for that. It's just the way things work, and we're not quite there yet. We will get there, and at the end of the course, actually not even at the end, hopefully in the middle of the course, when you read something in the research literature and you see p less than 0.05, you will know exactly what that means. It is the probability of something occurring, right? Actually, you know what? I'll tell it to what it is. It's the probability of something occurring by chance. That's what that means. Okay, and if that doesn't make a whole lot of sense to you now, don't worry about it. When you see something, blah, 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 here's some numbers, p less than 0.005, that means what the researcher is saying is that you see these values here that I just presented? Yeah, there's less than a 5% chance those things happen by chance. That's what that p-value is saying in the literature, but we'll get there. We'll unpack that more so. Okay, so let's carry on here and let's do a little bit of math. And the math isn't hard. It's some fractions. I said before, the statistics math, and I'm keeping it really simple for probability. The statistics math is simple. We're just going to work with some fractions today. So let's take a look at a few things. I want to take a look, we'll begin with flipping a coin. We'll get into rolling a die, right, or dice, I think is the plural for that. And then we'll talk about some other continuous variables and see what happens. And so we call this boundedness, what we call it's the sample space of a random variable. Just think about sample space for right now. And the sample space is defined as the set of all the possible outcomes in an experiment or in a sample, or in our case, flipping a coin. Because when you think about it, flipping a coin really is running an experiment, isn't it? Right? You're actually doing something to elicit an outcome. That's an experiment. So when I flip a coin, right, that's the experiment. And so what are the outcomes going to be when I flip a coin? It's either going to land heads up or it's going to land tails up, one of the two. And so within the sample space lie these numerical characteristics or descriptions of each one of these events. And this is called the random variable. Don't worry so much about these definitions. This is mostly kind of building on some of the nomenclature and building our scaffolding of knowledge here of how to calculate probability. And the numerical aspect of the random variable becomes a bit more important as we move through it. So this is just what it is. You've got your sample space, which is the boundedness, and then you've got your random variable within the sample space, and it tells you the number of possible outcomes within that sample space. And so here's what I mean by this when you start getting into random variables, right? In the sample space of the flip coin, you've got the numerical characteristics or descriptions is either going to be a 1 or a 0, because that's all that can happen. However, in the case of rolling a 6-sided die, the random variable can be either a 1 or a 2 or a 3 or a 4 or a 5 or a 6, right? There's one of 6 potential outcomes rolling a die compared to a coin flip where you've got one of 2. That's just it. You know, if it was an octagon or something, you would have one of 8, right, in that. So that's what we talk about, right, when we talk about the random variable within the sample space. All the random variable is it tells you the number of possible outcomes that can occur. And with a coin flip and a die, it's pretty easy. It's pretty easy to see what those possible outcomes are because they're very discrete, right? When we think of sampling people in research, because people are much more complicated than coins or die, then the random variable is equivalent to a measure from each individual in that sample. That gets much more complicated. I mean, how would you sort that out? Right? That's where you sort of get, okay, now this is getting beyond my capabilities, and I'm totally there with you, but we'll cover that as we move along. So we can break random variables down into 2 broad types. The first one is discrete, which we've already seen. That was the coin flip and the die. And then you get into continuous variables, and that's more like people, if you want to think about it that way. So let's take a look at examples of outcomes with discrete variables and continuous variables. So let's give a definition of what a discrete random variable is. It has a countable set of distinct possible values. And we've been kind of working through this already. Okay, so let's get into some of the calculations here, right? So how do you calculate probability? And again, we'll keep it really, really simple because it does get really complex. So very simple probability, right, involves the chances that a particular event will happen. And so we have to define these things here. So if we're sorting out what probability is, and if you see it in the literature, you might see something like this. P, and then in brackets beside it, you're going to see the capital E. So what do these values mean? P means the probability, and E means the event, right? So P in brackets E is equal to the probability of that particular event that is occurring. And we express probability in terms of fractions. And so here's what the probability of the event might be in terms of a fraction. Let's look at the denominator first. Number 1, on the denominator is going to be the total number of possible outcomes that could occur, Remember, you've got a series within the sample space, and within that random variable, you've got a series of potential outcomes, right? And the numerator is, they call it the number of favorable outcomes. I don't know why they use terms favorable for, right? It's the outcome that you think is going to happen, or the outcome that could happen. So again, you've got a fraction. Let's take a look at a coin flip to give an example of probability using the fraction below. Okay, so let's do an example here of a coin flip and work out the probability of, say, something landing heads up. So at the top here, we have our formula for probability. The number of favorable outcomes, in this case, we'll say heads is going to be our favorable outcomes, divided by the total number of possible outcomes. Okay. So to do the math, here what we have here, how do we know the chances or the probability that heads is going to show up? Well, I know there's only one option for heads. That's going to give me a value of 1, right? So I put 1 over the numerator as the numerator here. And then down below, I've got the total number of possible outcomes. And so I want to add up those total possible outcomes together. One of the outcomes is heads, which I'll give a value of 1 because that's one potential outcome. And I've also got the value of tails, which I'm going to give you a value of 1. When I add 1 and 1 together, I get a value of 2. And so my fraction is 1 heads out of 2 possible outcomes, either heads or tails. And when I convert my fraction to a percentage, it comes out to 50%, which makes sense. That's almost intuitive because we understand heads, and tails, right? And so there's a 50% chance that the coin will land heads up. So let's take a look at a die. Okay, so when I roll a die, there's 6 potential outcomes that can occur. 1, 2, 3, 4, 5, or 6, right? And so let's say that I want to know the chances that I'm going to roll a 2. What's the probability or chance I'm going to roll a 2? Well, let's use our formula again, right? So again, we use the same fractional formula. We want to establish what our numerator is. Well, we want to roll a 2. Now the thing, there's only one 2 on a 6-sided die, right? And so we don't give our numerator the value of 2, we actually give it the number of 2's that there are. There's only one 2, and that's going to be the outcome. So the numerator is going to be a 1. The denominator, as we said before, there's going to be 6 possible outcomes. I can roll either a 1 or a 2 or a 3, 4, up to a 6. Each one of these outcomes here gets a value of 1 because it's one potential outcome. But there's 6, right? There's 6 outcomes, 6 potential outcomes on the bottom. So I add up all those ones together, I get a value of 6. And so our fraction for the probability of rolling a 2, if it's a fair die, is 1 over 6. And I convert that to a decimal and then to a percent. There's a 16.7% chance that you're going to roll a 2. Now that's not very high if you ask me. That's actually pretty low. It tells me in terms of it, when I get to probabilities like this, it's a piece of information that allows me to make a prediction into the future. I don't like my chances for rolling a 2, right? Because the chances are very, very small. If you told me it was a 100% chance, not a problem. Right, I'll put $1 million on red number 2 or something like that and get my money back. But it's not. It's only a 16% chance. I don't like those odds. I don't like those chances. I don't like that probability. And so I may not put my money down. If I was a gambler, I may not put my money down on the 2. So let's do one more example with the die, then we'll move on here. So let's ask a different question. Same area, same arena, same lab. We're rolling the same die. Now, what if I ask you this question? If a fair die is rolled, what is the probability that you will roll a number higher than 2? Okay, that's a little bit different. Let's take a look at the numerator now. Now the numerator gets a little bit more interesting. How many values are higher than 2 on a 6-sided die? Well, there's the value 3. There's the value 4, there's the value 5, there's the value 6. All these values are higher than 2, and there's 4 of them. And so there are 4 potential outcomes that are higher than 2 that can occur. And so on the numerator, I'm going to write the number 4. The denominator, of course, stays the same because it's still out of 6, because that hasn't changed at all. And so what we have here is we've got 4 out of 6. If I convert that to a decimal, it's 0.67. So that tells me there's a 67% chance I'm going to roll a value of 3 or higher, because 3 or higher is higher than the value of 2. Now my odds of getting that favorable outcome, at least to me, have improved dramatically, almost by a factor of what? Almost by a factor of 6, right? Maybe not quite 5. Actually, less than that, 4. Anyway, my odds have improved, or the chances of rolling a value higher than 2 have improved. So let's move on from discrete variables into something a little bit more trickier, which are the next set of random variables, and that's continuous random variables. And continuous random variables are those that have any value to any number of decimal places that fall within some specific interval, right? That it can have any value to any number of decimal places that can fall within some particular interval. You know what that means? That means that there's a lot. As a matter of fact, even if you set your boundedness, like I have in the example below, with 150 to 250 pounds, can you imagine how many potential outcomes there would be if I said, okay, I want you to pick a weight or an outcome of a weight that goes to 3 decimal places? You're talking about thousands and thousands and thousands of potential possible outcomes, right? So it gets a bit trickier here. So let's take a look at the example here. Suppose the fire department mandates that all firefighters must weigh between 150 and 250 pounds. The weight of the firefighter would be an example of a continuous variable, right? You can't slice that salami thin enough, right? There's a ton of different outcomes. Why? Since the firefighter's weight could take on any value between 150 and 250 pounds. Okay, so you have this almost like this smear of potential outcomes now that you've moved away from a discrete variable to a continuous variable in this case. Okay, so it gets a bit, it's hard to kind of bridge this here, but let's just kind of go on to this question down below. Sometimes, and this might be of interest to you as a researcher, you may want to know what are the chances, or what is the probability that a firefighter's weight will be more than 172 pounds, given a range of 150 to 250 pounds in a particular population of firefighters. Now, that may be a question of interest to you. I've put on here, who cares? Well, it depends upon what the researcher wants to know. But these are the types of questions that we ask now. So we don't have to worry so much about going to decimal places. You might be overwhelmed by the amount of data. When we get to the normal curve, we actually do a little bit of a conversion of the values that makes it a little bit easier for us to understand this and easier for us to use it. But these are some of the questions that researchers do ask. What are the chances that we're going to find this in this particular range of values? Right? The case I've given you here, for whatever reason the researcher might have, might have to do with measuring some value of overheating. There might be some relationship with weight and overheating in firefighters when they're on the job. They want to find that association. So we want to know how many firefighters, on average, right, or the probability that firefighters are going to be over 172 pounds. Can we determine a probability of that? What are the chances if I take a sample from a population of firefighters in that sample? I might find that, well, 30% of the firefighters are over 172 pounds. Okay, that gives me a sense of who is in the population, at least in terms of weight. So these are kind of descriptive statistics, but really they become more inferential statistics a little bit later on, because if we know that 30% of firefighters are above the weight of 172, that might have implications for my research. You might be wondering at this point in time, what is my fixation with variables, and why is Mike confusing my life once again by backtracking here and describing these continuous random variables? Well, again, let's just pull back a bit and remember what we're doing in statistics in terms of context, right? A lot of statistics is all about inference, right? We take from a sample and project onto the population those particular characteristics or findings about that sample. And ideally, the sample is randomly chosen, although a lot of times it's not. It can be a convenient sample. And one of the things we have to remember is, unlike really nice, clear-cut variables like flipping a coin, or answering yes or no on a survey, or flipping a die where I've got an option, 1 through 6, very, very clear-cut options. A lot of the measures that we use in survey research and in population research and in quantitative research are continuous variables, and these variables are interval and ratio. And so how then do we answer the question, what is the chance, for example, that someone is going to, if I'm measuring weight, for example, what are the chances that that person is going to be 171.5 pounds? And it gets a little bit more tricky where we start looking at the probability of these continuous variables or a value within that continuous variable being showing up. So still sticking with continuous variables here. Unlike discrete variables with outcomes that are more clearly defined, yes or no, heads or tails, 1, 2, 3, 4, 5, 6 on a die, when we measure continuous variables, that is to say interval ratio variables, we often see this spread or dispersion of scores. This is what we see. Nothing discrete. We see that smear or dispersion of potential scores when I measure something from a sample that is a continuous variable, right? And we've seen this before. We saw that in chapter 4 with histograms. When I take a measure from a sample, for example, and it's a continuous variable, what I see is I begin to see spreads of scores that look like this. It's not just 1 or 2 or individual 1, 2, 3, 4, 5, 6. There's actually a series of values that can occur. I take a sample of 50 people, I measure them on height. Not everybody's going to be the same height. There's going to be a spread of scores of height, and if I put them into class intervals, I now begin to see this spread of scores. So again, just before we move on, let's take a look at what we've done here. And we again are looking at potential outcomes depending upon the type of measures that we use. So I've got my 2 examples here of discrete random variables. Here's my heads or tails. That's going to be what we call a nominal or a dichotomous variable. And I've got 2 potential outcomes, either going to be a heads or a tails. So the probability is pretty easy to work out with that. My die is, I guess you could classify it as an ordinal variable. You could also make the argument it's nominal. Nevertheless, it's still a discrete variable, and I've got a chance of one of these 6 values showing up when I roll a die. When we get down to the bottom here, we get into the continuous variables. Now, because they're it can be any value within a certain range of values, what we begin to find is no longer is it nice, clear, and cut and discrete, right, individual scores, but rather I get a smear of scores, right? And so the question now becomes, what does the smear look like? Is the smear going to look the same all the time? If I keep measuring the same thing, if I keep drawing different samples out of the same population, will I still get the same smear of scores or the same dispersion of scores? Okay, let's unpack that in the next couple of slides coming up. So let's take a look at one of these dispersions of scores, and let's keep to the same ones that we've seen before. So we're not going to change things up a little bit. So we've seen before, in chapter 4, we took a look at histograms, and in particular, we took a look at diastolic blood pressure, right, in a particular sample size. So I think this example here was a sample size of 56, and we measured them. We had all their individual continuous data points, and what we did was, to make it a little bit easier, we put them within their own little class intervals, and then we graphed them. And what we saw was a particular pattern of data. And I want to highlight this to you, patterns in data. And one of the patterns that we see, and this pattern occurs fairly frequently, is this histogram that kind of looks a little bit like a pipe organ, or I think I said before in the previous PowerPoint, it looks a little bit like Ragnarok, right, from the Thor movie, that big castle, so to speak. But we see some patterns that begin to occur with these spreads of scores that we see in these continuous variables. And what we see here is on the ends, again, this might be a bit of a repeat, we see very few scores on the ends, right, of the scores, and most of the scores are kind of congregated in the middle. And so this is the funny thing that we see when we start pulling samples out of populations and measuring them on the same variable, is we begin to see the same type of pattern that emerges. A pattern very similar to this. This particular pattern that we see, again, looking back at the same blood pressure distribution pattern, where you have few scores happening on either end of the scores, very low scores, very few low scores, and very few high scores, and most of the scores kind of congregated in the middle. We see this in many data sets, and we see this in real-world variables, things like weight, height, average salary, grades in some cases, those types of things, right? So we begin to see these patterns in data, and the question then becomes this: instead of saying, what are the chances I'm going to roll a 1 or a 2 or a 3 if I'm rolling a die, or what are the chances I'm going to roll a heads? What if I'm going to do a coin flip and it's going to be a heads or tails? The questions now become, what are the chances I'm going to have a certain number of scores on the low end or the high end, or what are the chances I'm going to have a certain number of scores in the middle of this dispersion of scores? And so we kind of extend the question a bit in terms of probability. What are the chances a score is going to fall somewhere on this dispersion of scores? And I know that sounds a little bit complicated. You might be thinking, oh my goodness, what is the math going to be to get us there? Well, the beautiful part and the beautiful extension of what we're getting into next is we're not going to have to worry about the math so much. Okay, you don't have to worry about the complicated math to determine what the chances of a score falling either on the high end or low end or middle, because we already have something worked out. And if you want to think about it as a template that we're going to be using, and that template is the normal curve. And so the next set of slides, what we're going to do, or the next section in chapter 8, we're going to springboard off of here and take us into the normal curve and show you how you can use the normal curve to determine things like the probability of certain scores occurring on a spread of scores. Okay, just a quick summary slide here, then we'll leave and we'll go on to part 2 of chapter 8. So here's our summary of this section here. Number 1, events can happen by chance. We know that. Things that occur can happen by chance. We have to accept that, right? We can measure occurrences by breaking them down or by giving them specific nomenclature. So for example, we can have discrete random variables. If I know the number of distinct possible values, right, dice, city of birth, I can actually work out a probability or a chance of something occurring using those discrete values, right? Continuous probability, again, is a little bit different because now we're looking at a spread of scores, right? It could be any value to any number of decimal places within a certain interval, right, that can occur. And so we begin to take a look at continuous probabilities not as discrete values, but rather as dispersions of scores. And we see that with histograms. Right. So sampling continuous variables results in a spread of scores that, as we're going to see, begins to resemble more of a curve, right, instead of clear discrete scores.